Hi everyone, I'm Rhea and this is Kruti, and our project is called Boulder Move. The main idea of this project is to give people in Boulder one intelligent dashboard where they can plan trips using walking, driving, bicycling, and public transport together instead of separately. We also pull in real-time weather and nearby events so we can warn users about things like storms, snow, or concerts that might slow them down. On top of that, we show everything on a clean interactive Google Maps interface and use a machine learning model to estimate the chance of arriving on time and how much delay to expect. The goal is to bring routing, weather, events, and ML predictions into one unified experience instead of many disconnected apps. On the front end, we use React, JavaScript, HTML, and CSS to build the map UI and all the user interactions. For the backend, we use Fast API, Unicorn, and Uvicon, and integrate external APIs like Google Directions, Ticketmaster for events, and Open Weather for the weather data. For routing, we relied on OSMNX for walking graphs, Raptor for transit routing, and Network X to manage the network. Our data comes from the GTFS transit feeds, weather API, and event polygons. On the infrastructure side, we deployed using Docker onto a Google Cloud VM, and Cloud Run used cloud storage for artifacts and Cloud SQL, PostgreSQL for trip history. All of this runs on a compute engine VM and with enough CPU, RAM, and disk to handle graph data and GTFS files. At the very top, we have the user. They open the Boulder Move web app in their browser and enter an origin, destination, and time for their trip. The request first hits the React front end, Boulder Move app. The front end handles the map UI, search boxes, and route cards, validating the inputs, which are the origin and destination, packaging everything into a clean JSON request. Once the user clicks plan trip, the React app sends a trip request down to the backend. The fast API routing backend on compute engine reads the origin, destination, time, and user preferences, calls different services to get transit routes, weather events, and fallback routing. It also calls the ML service to get an on-time probability score, combines everything into one response, and sends it back to the front end. Now let's talk about the routing engine, the OSMNX, and the Network X and Raptor. This is our transit routing engine. We pre-built a transit graph using the GTFS data, using OSMNX and Network X, and we use the Raptor algorithm to compute the best public transit routes. When the backend needs transit options, it calls the engine. The next we talk about the Open Weather API. This backend calls to fetch real-time weather routes along weather events along the routes. We care about these things like heavy rain, snow, and extreme temperatures since they affect walking, biking, and transit reliability. The Ticketmaster API provides events data, concerts, games, and festivals. Events cause traffic on transit or transit crowding. The backend queries this API for events near the route or near the origin or destination. The Google Maps Directions API is our fallback routing for driving, walking, and bicycling, or when our custom engine cannot find a good enough transit route. If needed, Fast API asks Google for directions and then merges those results with our own transit routes.
To see Cloud SQL, the Postgres trip history data. This is where we store trip history and performance data. Which includes basically what routes we offer, which route the user chooses, whether the route ended up on time or delayed. Now, the data is being ingested, the performance data is being ingested into our Cloud SQL, and this becomes our database and the training data set for our ML model. On the top right is our training side, okay, which is separate from our live app, a dedicated VM where we run offline training jobs. It pulls the historical trip data from Cloud SQL and transforms it into ML features, and it trains the XGBoost model, which is then uploaded to our Google Cloud storage. This is a long-term storage for the latest production model. The model file sits here, ready to be loaded by the online ML service. The image is then pushed into the artifact registry, which is Google Containers Registry. When the ML features are pulled from our model, the model is loaded, and the response is sent back to our Fast API backend, which shows us the prediction for the time uh, on which the return time probability.
For debugging, we spent a lot of time making sure the whole system worked end to end. First, we reproduced bugs systematically and used logs, the browser console, and the network tab to see exactly where things were breaking. On the front end, we fixed a lot of React syntax and reference issues like missing commas, broken template strings, and is not defined errors, so the app could build cleanly again. We also updated our Google Maps and place autocomplete usage since some older methods were deprecated and adjusted the layout of them so the map markers and the input actually rendered at the right size. On the backend, we aligned the JSON schema, fixed file paths for data, cleaned up environment variables. We also had to use git remote and branches resolve merges as and fix npm run build plus nginx issues. Finally, we verified the GCP setup, VM endpoints, cloud storage, pubs up, so all the services could talk to each other correctly.
For the training and testing, we treated Boulder Move like a real system that users would rely on. To train the system, we built a small database of real Boulder trip cases and defined what a reasonable output looks like in terms of routes, weather, overlays, and event information. We then improved both the front end and back end by checking these examples and incorporating feedback about what was confusing or missing. For testing, we had three levels. At the unit level, we tested routing functions, GTF lookups, and the weather and event modules individually. At the integration level, we tested the full plan trip request and checked that the map rendered correctly and the route cards matched the backend response. And at the end-to-end level, we tested the complete flow. The user enters origin and destination and a full route with alerts appear on the screen.
Now let's walk through a quick demo of our Boulder Move system. This is our Boulder Move Smart Trip dashboard. On the left-hand side, you can see the trip setup with origin, destination, and stops input fields. All of these input fields have been use autocomplete so that we do not have to check the redundancies or pre-process our users' input data. Now, as you can see, once I enter the source and destination, you can choose the different modes of transport and the Google Map auto reloads. The different modes of transport below are mainly transit, bicycling, walking, and driving. Anytime these different modes of transport get triggered, our Google Map reloads, and you can also see alternative routes to reach the same source and destination. Along the route, it also shows you today's weather and any kind of event alerts on the left-hand side. Below, you can see all the different routes and the different weather alerts on those particular routes.
Now, let's go through the most important feature of our system, the transit mode. When I switch to transit mode and plan a trip, the routes you see here are not just coming from Google. They are actually computed using the GTFS transit data that we downloaded from the RTD website, which is uploaded on a Google Cloud VM. That VM is responsible for computing fast, realistic transit routes using the bus and train schedules from the RTD. All our historical trip data and route features are stored in PostgreSQL on Cloud SQL. We use the data to train a machine learning model that predicts whether you are likely to reach your destination on time. For training, we use XGBoost as our ML algorithm. The training code runs inside a Docker container, so the environment is consistent. We build that Docker image using Google Cloud Build, and the trained model file is stored in the Google Cloud storage. Now, Cloud Run takes a Docker image, scales it automatically, and exposes an HTTP endpoint. Every time a user requests a route in transit mode, our backend sends the route features to this Cloud Run service, which returns a prediction of whether the user will reach on time. We display that prediction along with the route details. We've also integrated a weather alert system. So, for example, right now it's snowing. So, our alert system shows that the snow on the route can cause significant delays. Other than that, we've also added a check for events along the route today, and it also subsurfaces upcoming events that take place on other days on the route. It also gives you all the events for the alternative routes. That way, the users can plan their trips ahead of time, for example, avoid extra congestion near a concert or even discovering events they might want to attend. So, this is what our entire system does. Thank you. This slide talks about how the system scales and where it might struggle. In terms of capacity, our React frontend can handle many users at once, since it's static and offloaded to the client. The fast API backend running on an E2 medium VM can handle around 20 to 30 routing requests in parallel, while the ML service on Cloud Run can auto-scale when load increases. Cloud SQL manages scaling for trip history and metadata. For bottlenecks, the main ones are the CPU on the VM, because heavy routing computations with Raptor and GFTS can be expensive. Cloud SQL can also become slower during spikes in queries. And finally, we depend on external APIs such as Google Directions and Open Weather API, so their rate limits and response times can also slow down our system. To wrap up, Boulder Moves brings routing, weather, events, and ML predictions into a single dashboard so people can make smarter travel decisions in Boulder. Thank you for listening.